Welcome back, everybody. So we are in section 6.2. We're going to start covering volume here. And it's going to be in the reverse order of what we did last year. So we're going to start with the volume of an area with a known cross-section and kind of a more generalized expression of volume. And then we'll discuss disks and washers. So to start here, you can kind of read through the notes here, but what we're going to be essentially generalizing is if we want to compute volume, volume is always going to be represented by base area times height. So they just use A for the base area. So in our integration then, if we have an area function that serves as our base area, then our height is going to be that differential. All right, so that differential, that infinitesimally small little sliver, because we're just going to take each one of these shapes and slice it into smaller pieces, right? An infinite number of smaller areas where we're calculating each individual volume and summing them together. So just below, they kind of give you this funky looking shape here, where it's like a piece of bread, and they're slicing a cross-section, so there's your cross-sectional area. And so we can do that along the interval A to B, and then we can add more and more slices, which will be adding more and more subintervals in order to compute the volume. So here we can see if they've sliced it into 7 subintervals. Right, that's going to give us an approximation of the volume, and then we could do 700, 7,000, 7 million subintervals, right, where each time we're getting slightly better approximations. And so we can say that the volume is approximately that area at x sub I times delta x for each individual, as your book calls it, slab or piece. And then adding up all of those volumes will give us the volume of the entire figure. Okay. So we've got our definition of volume there. So the key for us, of course, is that we want to figure out A of x. I want to figure out what is the area function for the solid that I'm describing, and we'll do it with nice figures, of course, for us. So it's going to be triangles that are, equilateral triangles, isosceles right triangles, squares, rectangles, semicircles, and ellipses. And then from there, we're going to, discuss disks and washers, which are going to be where we have circular areas. So these are going to be areas where our region is circular, and so our base area is going to be pi r squared. So pi r squared times delta x will be our volume. And we're also going to have washers, where we have those small flat rings called washers, where we subtract the greater volume from the smaller volume in order to get the ring shape that we're looking for. So you can look through the notes here to remind yourself of those methods. And then we can just, jump into some examples here to review how we will evaluate these. So we've got the volume of a solid obtained by rotating the region bounded by y equals 1 minus x squared and y equals 0, which is just the x-axis, about the x-axis. So let's go ahead and start with this. Key is always going to be to graph. Right, so you always want to graph your region. So we've got 1 minus x squared is going to look like this, and that we're bounded by y equals 0 and our curve. So be careful, because you might say like first quadrant or x equals 0 and y equals 0, but this just says y equals 0 and y equals 1 minus x squared. So our entire region here then is going to be what we are rotating, and we're rotating it about the x-axis. So again, I would recommend drawing a little curly arrow to indicate how we're rotating it. And from there, we're going to figure out, okay, am I going to use disks? Am I going to use washers? All the examples today are going to be of that form. We'll do the shell method in 6.3, but clearly here we can see that as we rotate the figure here, it's going to be creating a completely solid figure, so there's not two curves or two radii that we're going to have to worry about. So we'll just note that we're rotating about the y-axis. So the axis that we're rotating about, we measure vertically or horizontally, depending on our orientation. And for discs and washers, your cross sections will always be perpendicular. So it should always be a perpendicular line from the axis of revolution. And this is our radius, right, which is just 1 minus x squared. So we intersect the axis at -1 and 1, which means that our volume is going to equal the integral from -1 to 1 of pi times 1 minus x squared, quantity squared. Now keep in mind, with your integrals, you can always just factor out the pi. And then we'll have, let's just distribute 1 minus 2x squared plus x to the 4th. And then from here, you can evaluate the integral. I would recommend, since we've got a, again, even function symmetric about the y-axis, we can make our calculation a bit simpler by doubling the volume of just 1/2 of the figure. So we'll get x to the 4th minus 2x squared plus 1 dx. And again, you can evaluate that on your own and see what you end up with. For the second example, we've got volume of a solid obtained by rotating the region x equals 2 rad y, x equals 0, and y equals 9 about the y-axis. Okay, so we can just note y is just 1/4 x squared. So we're just going to be a parabola that is going to be compressed a little bit. And it's going to be the positive version, though, so it's only going to be on the right side of the axis, of the y-axis. So let's go ahead and graph this. So we've got 2 rad y. And that's x equals 0 and y equals 9. So we're bounded x equals 0 and y equals 9. Okay, so it looks like our region is going to be in here, and we're rotating about the y-axis. So again, we draw our cross sections perpendicular from the axis of revolution to our curves. So that's going to be our radius. Radius is equal to 2 rad y. So then your volume is going to be the integral from 0 to 9 of pi times 2 rad y squared dy. So we're going to end up with 4 pi as our coefficient. And then this becomes a really easy integral. So it's just going to be y dy. So we can just work this one out. So we'll have 1/2 y squared, 0 to 9, which is going to be 4 times 81 pi all over 2. So I think it's 162 pi. Because these will cancel and multiply by 2. And then for number 3, whoops, we've got, two interesting curves here. We've got the absolute value of x and the absolute value of x cubed. So let's take a look at what these are going to look like. So absolute value of x is pretty simple. Whoops. And then the absolute value of x cubed. So x cubed we know on the left is going to look like this. And then that normal part that curves that way is going to be flipped so that it looks the same on either side, I think. Yeah. So it's going to look something like this, and so then our region is going to be 2. There's going to be 2 regions. And we have symmetry about the y-axis, so again, we can use that even symmetry. So let's go ahead and figure out where they intersect. So absolute x equals absolute x cubed, if x is plus or minus 1, obviously. Okay. So then, and we're rotating about the x-axis. Okay, so rotating about the x-axis. And so now we're going to have to use washers, because clearly we've got 2 curves here, and we need to take the larger volume and subtract the smaller volume. So just note that from our axis of revolution, our smaller radius is going to be to the blue curve, and our larger radius is going to be to the red curve. So little r is going to be the absolute value of x cubed, and then big R is going to be the absolute value of x. So big R and little r. And now we just need to figure out our volume expression. So volume is going to equal the integral from -1 to 1 of pi, and now we're going to have r squared minus r squared, so absolute x squared minus absolute x cubed squared, which, when you think about it, we can actually just drop the absolute values if we're squaring them, because they'll always be positive. We don't have to worry about negative values, but we'll leave it as is for now. But again, if we wanted to use symmetry, we could multiply by 2, bring the pi outside, and just integrate 0 to 1. And it's going to be x squared minus x to the 6th. And again, I'll let you evaluate that one on your own. Now you might think about, what if we did the same curve in the first quadrant about the y-axis? So that would be a function of y version of this. So you might think about that one. Let's see. So I think we'll do these last 2, and then we'll talk about volumes of known cross-sections next time. So here we're just going to set up our region. We're not actually going to evaluate the integrals, but we want to set them up. So we've got y equals x cubed, and then a quadratic, y equals x minus 1 quantity squared plus 1, about y equals 10. So now we're going to rotate about something that's not just the x or y axis. All right, so for A, I want to draw a graph here. So we've got x cubed and x minus 1 squared plus 1. So there's our parabola. And then there is our cubic. We should probably add in x equals 0 here as well. So what we're looking for is this region here. So if I want that region inside, I'm going to need to figure out what I'm rotating about. So that's y is 10, okay. So 10 is somewhere above. Clearly it's going to be past the intersection points, right? So if x cubed equals x minus 1 squared plus 1, these are going to be equal to each other at 1 and only 1, I think. Yeah. So you can verify that 1 is equal to 0 squared plus 1. So their intersection point is going to be at 1. And so from there, we've got our curves. And so we'll draw in our, let's do green. Draw in our axis of revolution. So here's y equals 10. So again, we're going to measure from our axis of revolution. So we're rotating this way. So our radius is going to be the red curve for the inner radius or the smaller radius. And then the bigger radius is going to be to the blue curve. So it looks like little r is going to be 10 minus x minus 1 squared plus 1. And then capital R is going to be 10 minus x cubed. So now we're measuring from y equals 10. So 10 is kind of our top curve. So we're still doing a top minus bottom expression for r here. And then we just need to figure out our volume expression. So for volume, it's going to be pi integral 0 to 1 of 10 minus x cubed squared minus 10 minus, it's going to be, going to move it down here, 10 minus quantity x minus 1 squared plus 1 dx. So kind of a long integral, would definitely be messy to do by hand, so definitely not one that we would want to do by hand most likely. But the key is the setup. I want to make sure that the setup is familiar for you. The second one then you can do on your own, just follow kind of the same format. This is going to be a little bit different though, because we're going to be rotating about a vertical line. So it's going to be a function of y, but the same idea will apply. And again, you can check the notes online. So next time we'll get into volumes of known cross sections. So if you do have any questions, shoot me an email, come by office hours. And so until then,